So our next speaker is the famous black hole photographer, Professor Katie Bouman. She is the professor of computing and mathematical sciences at Caltech and Rosenberg Scholar, and also has courtesy appointments as a faculty in the electrical engineering and astronomy at Caltech. And she is joining us, I believe, from a conference in Italy. So
thank you. Yeah, thanks so much for the kind introduction and for organizing this workshop, George. I've already learned a lot from great talks from Yi-Sung and Cynthia, so I have a lot of questions for that. But today I'm going to actually be talking about interpretability in a slightly different way. I'm going to talk about how we can use machine learning tools to help with interpreting complicated data we get from scientific experiments. So back in 2019, the very first image of this black hole was captured. And this image showed for the first time how light from hot gas was being bent around a black hole in the galaxy M87 to form this ring of light. And so recovering this image took an international team of scientists and engineers over a decade to build a computational telescope that made it possible to see structure on the scale of the black hole's event horizon. And getting this first image was a huge milestone, but really it was just the beginning of what we're after. And so this image kind of demonstrated that it was possible to study via imaging the environment around a black hole. But now that we have this new kind of extreme laboratory of gravity, we're really thinking towards the future, and we're trying to think of ways that we can improve our instrument and algorithms to learn more. So today I'm going to focus on the future of black hole imaging and how developing methods to improve interpretability will play kind of a crucial role in helping to extract new science from future data. So first I'm going to talk about an approach we've been developing to better characterize the confidence or uncertainty of structures in image reconstruction, which will lead kind of to the ability to reduce the time to science in the future. And then also I'll be talking about an approach we've been developing to extract information not just about the static structure around a black hole, but actually the stochastic motion of lens gas around the black hole. So both of these approaches are inspired by a desire for interpretability in our solutions. So as I said, I'm not going to be talking about interpretability in the sense that kind of people normally describe it, but more like how can we use machine learning to help with interpretability? Okay, great. Before getting started though, why is taking an image of a black hole so difficult? Well, since the black hole in the galaxy M87 is 55 million light years away from us, this ring of light is incredibly small in the sky. It appears about the same size as a grain of sand, but if the grain of sand is in New York and we're viewing it from Caltech in California. So it's incredibly small, and it turns out taking an image of something that small would require using a traditional telescope that is, the size of the entire Earth. And since this obviously wasn't possible, we had to get creative and did the next best thing. We connected telescopes from around the world to work together and act as a computational telescope the size of the Earth that was possible to resolve structure on the scale of a black hole's event horizon. But, the question is, how do you make an image then if we don't collect light across the whole globe? Well, there's a lot of holes in the data, and that means that the measurements we collect are sparse. And once we've collected these measurements, our goal is to invert them to recover a picture back. And if we had tiled the globe in telescopes, and we would have gotten these dense measurements, and so the problem would have been a lot more trivial. But because of the sparsity of the data, that means that there's an infinite number of possible images that are going to be consistent with the data we measure. And so this makes the problem, this sparsity, and also the extreme noise that we experience, makes the problem of recovering an image really challenging. So how do we solve it? Well, of the images that are consistent with the measured data, some images have structures in them, have image statistics that we think of as more desirable. And so therefore our goal becomes to find an image that doesn't just fit the data, but is likely under some sort of mathematical model of a good image. And so using this idea, we developed techniques that allowed us to inject preferences for image statistics in the pipeline and use this to whittle down from the infinite possibilities to one solution. All right, so in a super hand-wavy way, I just told you how we can go from sparse noisy measurements from the telescopes to an image by injecting image preferences. how do we write that kind of mathematically? I think it's just useful to see mathematically for some of the connections later on. So one way we solve it looks like this. We solve an optimization problem where we're trying to find an image X that maximizes a posterior probability of the image conditioned on the observed measurements Y. And by simply rewriting this using Bayes' rule that you've probably seen in your probability classes and stuff, we can see that maximizing this log posterior probability is equivalent to maximizing the sum over the data log likelihood and a log image prior. So just those two terms that we just discussed in a really hand-wavy way before. And we refer to this strategy as regularized maximum likelihood. All right, so how do we actually go about solving this optimization problem? Well, in imaging problems, X here, the image that we're after, is very high dimensional. So it's standard to do something like gradient ascent to solve that. But the challenge is that one, gradient ascent, you often can get stuck in a local maxima. And two, even if you're super lucky and find the global maxima, there's nothing to say that there isn't like another solution there that's almost as good that you also shouldn't be considering. And so this ends up being a significant challenge for a lot of imaging problems, but especially for black hole imaging where this energy landscape is very non-convex. So for example, on the left side here is a synthetic image of a black hole. And we took this synthetic image and we generated telescope data from it as if the Event Horizon Telescope were seeing this image in the sky. So we're making fake telescope data. And using this mock data set, we ran our typical regularized maximum likelihood methods on it to see what we got. And we noticed that every time we ran the method with a slightly different initialization, we would recover different results. In some of the images, you can see that the bright spot recovered is in the top right. And in some cases, the bright spot is in the bottom left. And if you try to evaluate the data likelihood for both of these types of these modes, actually it appeared that both modes fit the data pretty well and you couldn't tell which one was the correct one. And so this is not that rare of occurrence actually, because of the kind of crazy noise that we experience on our measurements, we have to solve a non-convex optimization problem that sometimes has multiple solutions like this. And so this can be a bit scary, right? Because it means that we had to manually explore the energy landscape in order to even see this multimodality. And if this was real data and we didn't do this properly, we didn't explore it fully, we could be missing out on an image that could lead to a totally different scientific interpretation. And so for problems like this, it's important that we have ways to efficiently visualize this space of possibilities. In other words, instead of computing a point estimate like we do with the regularized maximum likelihood, where we're finding the best image, we want to be able to instead sample from a full posterior distribution, that probability of X, the image, given Y, the measurements. And this is important in order to visualize the full space of solutions that is possible. So oftentimes, posterior estimation is achieved using sampling methods like Markov chain Monte Carlo, but these sampling and rejection methods like in MCMC can be prohibitively slow and computationally expensive when you're working with high dimensional inverse problems like you need to do when you're solving for X here, which is the size of an image. It's very high dimensional. And so to tackle this, we've recently been developing new methods for efficient posterior exploration by exploiting deep learning machinery for the purpose of being able to visualize the uncertainty in our results. In particular, our aim was to learn a deep generative model to approximate the posterior samples of an imaging inverse problem. So let's start by reviewing just very briefly like what the deep generative model. You'll see why in a second. So I'm sure most of you are familiar with the great success of deep generative models in computer vision. Perhaps you've even heard of them in the news. These deep fakes are everywhere. So what are these generative networks? Well, given enough training images, we can train a neural network that takes as input random noise, and if you put this input of random noise, it will output a picture that looks like a real scene at first glance. And by plugging in different noise images, you'll get different output pictures. All right, so why am I telling you about this? Well, these deep neural networks define an implicit distribution over the space of images. And so these kind of impressive results that have come out of this community indicates that these networks allow us to learn very flexible and expressive distributions that capture very complex correlations in pixels. And so inspired by these generative models, my postdoc Hassan has been developing an approach to sample from a posterior distribution using a learned generative neural network. So the goal is to learn the weights phi of a neural network such that if you pass different random input noise, Z, to the neural network, out is going to pop a sample from the image reconstruction posterior. And different input noise should result in different posterior sample images. So essentially the neural network is just, you want it to learn a mapping from a noise distribution to the target image's posterior distribution. Okay, so how should we go about training the network to give us posterior samples? Well, unlike in the case of the bedroom generator that we just saw, we don't have a set of training images to use. If we had a set of samples from the image reconstruction posterior, then we would be done, right? Because there would be no need to learn a neural network to generate those posterior samples if we already have samples from the posterior. So the only data that we have to work with is the sparse and noisy measurement data, Y, that we've collected from our instrument. So it's a kind of like an unsupervised learning problem then. And so in our approach, which we call deep probabilistic imaging or DPI, instead of using this collection of training images to solve for the neural network weights, as is typically done in computer vision problems, we instead found that we could define the loss that is minimized when the weights of the neural network result in a distribution of generated images. So the neural network produces a distribution of images that best matches the true image posterior. And we can do this by actually minimizing the KL divergence between these two distributions. And so actually solving this ends up resulting in a very specific type of this is a specific type of variational model. And so in variational methods, what you do is you define a very simple family of density functions. For example, Q phi here, which is being visualized by the blue space of possible distributions. And for every phi, that's going to result in that indicates a full distribution here. And then what we do is we solve an optimization problem to find the parameters phi that best match the target posterior distribution we're after. So where that target posterior is shown by the yellow star here. So the question then becomes, what should this family of variational distributions be that we're searching over? And traditionally, typically people searched over very simple distributions like Gaussian distributions because you needed to be able to solve the integrals efficiently and evaluate probabilities. But in deep probabilistic imaging, when we use a neural network, we can actually define a very flexible family of distributions where phi here is representing the network weights. And this flexible family of distributions can actually better capture the image posterior distributions we're interested in targeting. So we're just basically giving ourselves more flexibility and hopefully getting closer to actually capturing the posterior that we're after. Actually, so DPI's optimization problem can also be intuitively derived by extending the regularized maximum likelihood estimation method. So it turns out that the KL divergence between the neural network's image distribution and that of the true posterior can be written as an expected log likelihood plus an entropy term, where this entropy term here that is added at the end actually just encourages the distribution to not collapse to a single solution. So you're trying to solve for a series of images that fits the data, fits the prior that we've defined, but also it doesn't just collapse to one image. And so that means in addition to understanding DPI as a variational inference method, it can also be regarded as a natural extension to doing uncertainty quantification for regularized maximum likelihood estimation problems. One last thing I want to note here is that in order to optimize this loss function, we need our generative model to be efficient in both generating samples and evaluating the likelihood of an arbitrary image. But normal generative models like GANs and VAEs are actually only good at generating samples, but you can't evaluate their likelihood to compute the entropy loss. So in order to accomplish both goals, we use an invertible generative model, a normalizing flow network, and this type of network can be executed in both directions. So we can easily generate samples using a forward pass and then compute the entropy loss using an inverse pass. All right, so how does this end up working? Well, let's go back to that black hole synthetic example I introduced earlier. So remember, for the ground truth image on the top, there ended up being multiple solutions that the regularized maximum likelihood would converge to when we would initialize with different images. And we tested our DPI algorithm on the data set and to learn that approximate posterior distribution. And once we had learned the weights of the network, we could just sample from it by passing in random noise and getting out different images. And on the bottom right are some samples from the learned neural network. And so you can see that the learned network was able to capture an approximate posterior distribution that also indicates there are two modes in the data. And it doesn't require, us to manually tune it or kind of tweak things to see if what the space looks like. It just naturally falls out. But perhaps kind of the most interesting thing is what happens when we run it on real data. So this is a result we got when we ran the approach on the real M87 black hole data. And so what this allows us to do is not just say not only are we able to recover the image of the light circling the ring, but it also gives us a measure of uncertainty, which allows us to understand that although the individual pixel values change across different posterior samples, and some areas do have more, are more constrained than others, since the standard deviation that we get here is, order of magnitude smaller than that of the mean image, we can also conclude that that ring is a very stable feature across all the posterior images. So this was very exciting to me when I first saw this result, since actually the very first time He ran the method on the real M87 data, he got nearly the same result that it took an entire group of people months to achieve through these grueling tests that we had done. And it only took about 1 hour of training time on a single GPU to measure the uncertainty. So I'm excited we're able to be making progress on methods that allow us to interpret our data by visualizing uncertainty in these kind of computational imaging systems. And as it turns out, we have found this DPI framework is not just useful for black hole imaging, but useful for many different types of problems. And so here are just a few other applications we've been working on in our group, from seismic tomography to exoplanet orbit fitting using the same kind of framework. But let's get back to the black hole. So, this image that we produced tells us so much about the immediate environment around a black hole and helps us get a better constraints on our understanding of gravity. But perhaps the most amazing thing is that by comparing the picture to simulations scientists have made for years, we found that the image we recovered is amazingly consistent with a number of the predictions that scientists had made. And so that was a really exciting thing. But you might have noticed that the simulation I just showed was actually moving. So you might ask, is the recovered image of M87 also moving? And in fact, it turns out it is. So when we collected the data, we actually collected over the course of a week. And so we collected 2 days at the beginning of the week and 2 days at the end. And we independently imaged each of these data sets. And so we had 4 images and we could string them together to form a movie. And when you play that movie, you can see that there's some evolution. So I'll play it for you here. It's really hard to see, so I'll play it for you again. You'll see that the bright spot kind of moves. It's at the beginning, it's more on the left, and at the end, it's more on the bottom. So studying evolution like this, like that we are starting to get hints of in M87, is really quite exciting. And that's not only, it gives us a window into the dynamics around the black hole, which helps us get an understanding of how these powerful galactic scale jets are kind of shooting out of the black hole. And it also helps us in mapping the space-time of a black hole, which will help in constraining our prediction of general relativity even further in the future. But actually, the black hole in M87 is not the only black hole we're interested in imaging to get a handle on the question of time variability. In the heart of our own Milky Way galaxy, 26,000 light years away from us, there's this cluster of stars. And by peering past galactic dust with infrared telescopes, astronomers have mapped the past of these stars over decades. And by tracking the motions of the stars over time, they concluded that the only thing small and dense enough to cause this motion has to be a supermassive black hole. And in fact, this discovery led to the Nobel Prize in Physics given last year for the work of Andrea Ghez and Reinhard Genzel for the discovery of a supermassive compact object at the center of our galaxy, which is otherwise known as Sagittarius Star. So as awesome as M87, the black hole in M87 has been, Sagittarius Star, or what we like to call Sag Star for short, might be able to help us better answer a lot of these questions. And since Sag Star is tiny compared to M87, that means the gas orbits around it much more quickly. So whereas it takes 4 to 30 days for the gas to make a complete orbit around the massive M87, for Sag Star, it makes a full orbit every 4 to 30 minutes. And so we'd like to be able to image these kind of very quick time variations around Sag Star, but doing so is difficult. And why is that? Well, actually the data that we collect to recover the black hole image actually has to be taken over the course of an entire night. And as the Earth is rotating, we collect different measurements that together we like throw into a big pot, and then we use that, all those measurements over the night to make the M87 image. But since Sag Star is actually evolving on the time scale of just minutes, that means that every measurement we make as the Earth is rotating is from a different snapshot of an underlying black hole video, not just a static image. And so how should we capture and learn about the black hole's evolution? Well, we've been working on ways to extract black hole motion we observe. And the first approach that we took was to develop methods to reconstruct full movies of the black hole evolving over time. But if you think that recovering a static image is a hard ill-posed problem, this ends up being orders of magnitude more challenging because we have the same amount of data, but we have to solve for all the pixels in a full movie rather than just a single frame. And so to get around this, you often have to include a significant amount of temporal regularization into the optimization problem in order to get a good result. But you have to crank up that regularization so much that oftentimes the reconstruction you're able to achieve is missing all those the rich dynamics that we're really after. And so here on the left is showing the synthetic ground truth video, and on the right, the video reconstruction obtained from this method, assuming some sort of measurements like synthetic measurements from an EHT style array. And so here we have recovered something like, the average structure, but the video on the right has lost basically all the information about how that gas is actually flowing around the black hole. And so although imaging is crucial in making sure we give ourselves the flexibility to see something surprising, perhaps, if our ultimate goal is to understand that ultimate underlying motion, it's not the right approach. Alternatively, you could also imagine wanting to describe the underlying flow using a physical model of black holes. For instance, we could search in the space of parameters that produce different synthetic black hole videos and try to find the parameter setting that best matches the data we've observed. And while this theoretically may be possible to do, in reality, this is too computationally expensive because simulating even just 60,000 static image snapshots for the M87 analysis we did took over 75 million core hours to complete. So this would be way too computationally challenging to be able to do. So there's this spectrum of different approaches that one can take in trying to recover the underlying motion of the source. On one end is recovering this non-parametric flow field, which gives us maximal flexibility, but requires us to recover a movie, which in the end is not even necessarily very interpretable. And on the other end of the spectrum is estimating the parameters of a physics-based black hole model. And while this would be maximally interpretable, this approach has the disadvantage that we're tied to this black hole model that's not even necessarily correct and therefore can be overly restrictive. So rather than just picking one of these extreme options, we'd like to find some sort of middle ground, use a model that kind of balances the pros and cons of these different approaches while still being computationally efficient. And towards that end, we've been working on modeling the persistent evolution of a black hole as the result of a stochastic advection diffusion process and solving for underlying black hole parameters that, that best fit the observed measurements and are still interpretable. So it tries to find an interpretable compression of the motion field by asking us to match only the persistent motion statistics. So this work is being led by Aviad Levis, a postdoc in my group, with collaborations with the black hole physicists David and Charles, and then as well as Joel Trop, who's in CMS at Caltech. So let's dive in to understand a little bit better. So here I'm showing the equation of a stochastic partial differential equation, which describes an advection diffusion process. Don't worry about like trying to you don't have to understand the equation. I just want to point out two things. There are these two parameters we really care about, V and D here, where V is the velocity field that describes how the bulk is moving, and D is the diffusion field, which describes how material spreads out in space. So for instance, these 2 cups of water here, they might contain different non-isotropic diffusion fields, which results in the dye spreading out differently in them. Therefore, you could kind of imagine describing the motion that we see in these two using a PDE like this with different underlying parameters D. So in this work, we use a black hole motivated fluid model to parameterize each of the fields. And then we can parameterize it with one parameter each, this theta1 and theta2. And by solving this equation for rho here, we can obtain movies that obey this advection diffusion process under different parameter settings. For instance, for this particular choice of theta1 and theta2, this input random noise produces a rho that has kind of this swirling structure. And by tuning these parameters appropriately, you can see that we can produce flow fields from this model that when paired with a physically motivated envelope, mimic that of a smoothly evolving black hole simulation. So our goal is to find the parameters theta here that best describe the observed source motion. But there's a catch, and that's that this is a stochastic PDE, meaning that the fluid flow movie that we get is dependent on that input forcing term, epsilon. And therefore, 2 random fields with the same underlying velocity and diffusion parameters result in very different pixel values over time. Therefore, a key challenge we have in estimating the dynamics is that the pixel values are driven by this unknown random source, and we don't want to have to estimate that. So inside of our work is that we could use dimensionality reduction to ignore this epsilon term altogether when determining the parameters that best fit the dynamics of the random field. So actually, I see that I'm running a little late on time, so I'm going to skip a little bit forward and just show that what you're able to do. So we basically compute a projection residual for different parameters. And by doing that, we can estimate what the underlying true parameters are with this kind of this loss function. And then we can use these more interpretable parameters, theta1 and theta2 that we learn, and use that, we can draw a sample fluid flow from the same parameters. And by merging this flow realization with the envelope that we learned simultaneously, we can optimize the parameters and generate a movie that we believe is sampled from a similar stationary distribution. Obviously this is very different. This fluid flow model is not a real model of black hole dynamics, but it contains a lot of the same properties. And so the big advantage of this approach is that these parameters we extract are still interpretable, even though they give us a lot of flexibility. And so by doing this, we can also fit to the measurements that we have. And we've been also improving the telescope array that we actually collect data from across the Earth, adding new telescopes in different locations to help us constrain measurements like this even more. The one I'm most excited about is we have a telescope that we're adding at Caltech's Owens Valley Radio Observatory to make Caltech part of the telescope as well. And by doing this, we're starting to see that we can improve these kind of, we'll hopefully be able to use interpretable methods like this to pull out parameters that we can then use to pull out scientific information about from this data, from sparse data. And so using an approach like this, we may be able to not just recover the general structure of the black hole in the center of our galaxy, but actually capture the properties of the gas as it circles towards the event horizon. And so to close, we've learned a lot from the image already, but what I hope I got across today is that, we're really just at the beginning. And as is the case in most fields of scientific imaging, to continue pushing the boundaries, it's going to become more and more important that we take advantage of emerging tools in machine learning and blend them with our understanding of physics to help with interpretability of our data. And so with that, I want to thank the amazing team of colleagues that I work with, but I especially want to highlight Ha, Sun, and Aviad Levis, who led these two projects that I talked about. Thanks.
Thank you so much, Kathy. There is only time for maybe one question now, but others may be answered asynchronously. And the question is, do you need to retrain your generative model for new values of data? Why?
Yeah, so every time we have a new data set, you train a new model. So every model gives a posterior distribution for only one data set. We are thinking about ideas of, though, how we can extend this to, for instance, let's say we want to change our underlying model. Can these underlying model parameters be tuned after the fact, and we train it, and then we can interpret and see how these model parameters affect the posterior that we get out in the end. But yeah, we learn one model, one neural network for one data set.
Thank you so much.